Hey, welcome back to Calculus. In this first section of chapter 10, we're going to spend a couple of days. In this first day, we're going to get introduced to an important notion called parametric equations. We're going to stick to parametric equations in the plane, so there are two coordinates in this class. In Calc 3, you'll look at parametric equations in three coordinates. So what are our goals for the lecture here? Well, I want to tell you what I mean by parametric equations. It's kind of a different way of defining or thinking about a graph in the plane. Today, we're going to take the point of view of the equations comes first, and then we're going to ask ourselves, well, what does the graph of those equations look like? In general, it defines some curve in the XY plane. And I want to give you some methods of determining the shape of that curve. Okay, graphs that are given by parametric equations have a direction. So I want to talk about what I mean by that direction and give you some ways of determining it. And then often, if you want to try to understand a set of equations that are given parametrically, understand their graph, one way you can do that is to revert back to a direct relationship between the two variables, and that's called eliminating the parameter. So I want to do some examples where we get a chance to do that. Okay, so I've got four examples lined up for you. And in each one, I want to kind of talk about, well, what does the graph of that parametric equation look like? What's its direction? And can we understand some of that stuff by eliminating the parameter, finding a direct relationship between x and y? Okay, so that's what's on the docket. Let's get started. I wanted to start by briefly kind of recalling what I mean by the graph of a function where one variable explicitly determines or is depending on the other. All right, so that is, what do I mean by the graph of something like y is equal to a function of x? Well, I draw the graph in the usual xy plane, and the graph has points on it, x comma f of x, and y is a point on that graph. Well, we choose the value of x, the input variable, if you like. It's chosen independently from the domain. So we pick that input variable, and then the function determines what the output variable y is. It's why we use the notation f of x. It's supposed to exactly tell us that this second number y depends on the first number x. And this picture, y equals f of x, is a picture of that dependence. All right. So we have one input variable x, we have an output variable y, and y depends on x. We write y equals f of x. And this graph, this curve in the plane, is a picture of that dependence. All right, so that's what we mean by the graph of a function. And by the way, there, that second coordinate y, we've used this terminology before, it explicitly depends on x. Right? If you tell me the x value, that function, that process tells me the y value. It's an explicit relationship between y and x. Okay, so what do I mean by parametric? I'm going to just slide up a little bit here. If I'm thinking of that curve, let's just keep looking at the same curve. If I'm thinking of it parametrically, well, then I think of both of x and y as being outputs, right? They're both output variables, right? So what's the input variable? Well, the input variable is some third variable called t. It's called the parameter, all right? So you can see it in my notation here. X depends on this variable t. I'm just calling the function and the output of it x. Y depends on this parameter variable t. Okay, so the point in the plane here, my x comma y, I'm just going to kind of color it blue to highlight it there. My x comma y, well, its first coordinate depends on this parameter variable t. The second coordinate also depends on the parameter variable t. So it's kind of a new way of thinking about the relationship between these two numbers. Instead of thinking of y as being determined by x, I think of x and y as both being determined by some third variable called the parameter. Okay, so those two functions together, those two equations together, they're called parametric equations. And the set of points in the plane, x comma y, where x is equal to x of t and y is equal to y of t, is called the graph of the parametric equations. So what I want to do with you guys today is give you some examples where I specify some parametric equations, and then I ask questions like, well, what's the graph look like? What does the graph of those parametric equations look like? All right, let's check it out in an example. It's a little bit abstract. So here I've got a couple of parametric equations. So my first function, x of t, is the square root of t. y of t is just t. Okay, so those are my two parametric equations. I have to give a domain for the parameter value t. So there it is. T is equal to or greater than or equal to 0. It has to be true to take the square root of it. Okay, so the question is, well, what does the graph look like? And when I ask that, I mean the graph in the xy plane. I'm always looking for these graphs of parametric equations to be drawn in the xy plane. So in particular, the parameter isn't present explicitly in the xy plane. You can look at the parametric equations individually. I can certainly graph in the tx plane the equation x equals square root of t. I hope that looks reasonable and familiar to you. Why is x on the a vertical axis? Well, because I'm thinking of it as an output. It's the output of the input variable t. The parameter is always the input variable. Likewise, I can think of the graph of y of t. That looks like a reasonable picture of the function y equals t, graphing y as a function of t, right? But neither one of those pictures is a graph in the xy plane. I want to know, well, what do the set of points x of t and y of t look like in the xy plane? We could kind of use this picture to do a little bit of investigation. Like if t is equal to 0, this is telling me that x is 0 for the x coordinates, so is y. The equations tell me that. Square root of 0 is 0, and 0 is 0. So I know one point, 0, comma 0, is on this graph. And in fact, I want to do that some more. It's the sort of first way I was ever taught how to graph functions, is just to plot points. Right? What did I just do? I just said, well, if you pick t equal to 0, those equations tell me that x is 0 and y is 0. So I plot the point 0, comma 0 in the xy plane. 0, comma 0 is the origin. There's no parameter in this picture. So typically what people do is just sort of write it in there as a label. So when t is equal to 0, I'm right there. 0, comma 0. I like to think of t as kind of time. You don't have to, but that's why I used language like when t is 0. All right. So likewise, let's do another calculation. When t is 1, well, the square root of 1 is 1, and 1 is 1. So there's another point on the graph. I'm just going to draw it like the scale is right here. That's my point, say 1, comma 1. And when is that happening? Well, it's happening when the t value is equal to 1. If you can read my messy handwriting in there. How about another one? I just picked a t value. I skipped 2 and 3 because they don't have integer square roots. The square root of 4 is 2. T and y is just t. So the next point that I'm going to plot here is the point 2, comma 4. So when, quote unquote, t is 2, excuse me, when t is 4, x is 2 and y is 4. So there's 3 points on this curve. There's 3 points on this curve. How could I get an idea of what the curve looks like? Well, I could plot more and more points. That's exactly what a computer does. So I've drawn over here on our graph the 3 points that we just plotted by hand. T equals 0, t equals 1, t equals 4. I just had a computer pick thousands of other values of t. And I picked so many, and the x and y coordinates are so close together that it gives the illusion of drawing this kind of smooth curve there. But really, that's just a picture of lots and lots of plotted points. So there is what my parametric equations look like. So it looks like that graph. But I might wonder, like, well, do I know this graph? Like, what's the direct relationship between x and y? What's the explicit relationship between x and y? So to answer that question, we do something called eliminating the parameter, right? So let me show you what I mean by that algebraically. I'm going to take this equation, y equals t, and I'm going to solve it for t. Theoretically, I could have solved the other equation for t as well, but it's sort of algebraically easier for me to solve that for t. And then I'm going to substitute that into x. So what do I mean by that? Well, x is the square root of t, but if t is equal to y, there's an explicit relationship between x and y. And if I square both sides, putting it in a slightly more familiar form, y is equal to x squared. So, okay, I recognize that equation. That's the equation of a parabola in the xy plane, right? So that same equation is the graph that we're looking at. Y is equal to x squared is the explicit relationship between x and y when x and y are defined parametrically by x is root t and y is t. Maybe a good question is, well, why isn't the whole parabola drawn? When I think of the equation y equals x squared, I typically think of some kind of symmetric curve around the y-axis. So where's this part over here? Well, that's missing because x is the square root of t. So the square root of a number can't be negative. So our x coordinates here are at least greater than or equal to 0. So that's why we kind of get half this parabola. Okay, so that's what I mean by eliminating the parameter. I solve one of the parametric equations for the parameter, I plug it into the other equation, and then I get a direct relationship between x and y. And maybe I recognize the graph from that direct relationship. Like here, like direct relationship is y equals x squared. I recognize it. Nice. Let's talk about direction here for a second. The direction of a parametric curve, this is a definition. So when I talk about the direction of a parametric curve, I always mean I let the parameter increase and I look at the points on the curve in that perspective. So in the picture that you can still see above, the parameter increases from t equals 0 to t equals 1. So I'm going to label the direction of the curve with a little arrow like that. So I think of the curve as being swept out or moved along, if you like, in the direction of the increasing parameter. If I sort of scroll back here, as t increases from 1 to 4, you would move along that section of the curve in that direction. So again, a nice kind of way to think about this. You don't have to, but you can think about x and y, x comma y as being the location of a point at time t. So it's one way to think about it. Think of x of t and y of t as the location of a point or a particle at quote unquote time t. It doesn't have to be time, but it's sort of one context. And so the graph is just the path of motion. The graph of the parametric equations is just the path of motion. Okay, and the direction is just the direction of motion. It's which way you move along that path. All right, I've got a Desmos window that I want to demonstrate this, but let's see. I've never done this in a video, so I'm going to try to switch over to Desmos while staying on my iPad here. So let's see if the technology is going to be nice to me. I'm just going to kind of make that a little bit wider. You can probably still see the notes on the left-hand side, but I know they're pretty micro there. But here in this Desmos window, I've got that parametric equation relationship graphed. I made a separate video that shows you how to graph parametric equations in Desmos, but you can always graph them. You can see up here, I can't do a laser pointer on it, but I just type in a point, x of t, y of t, and x of t is square root of t, and y of t is called t. And then it lets you choose a domain value for t. I picked 0 to 6. And then that middle thing, the square root of AA, is just so I have a slider. So because I want to just show you, imagine A here is my parameter. And so that little blue dot down there is where our particle is at the time t. And as t increases, see that blue dot is sweeping along the curve in the direction of motion. So I just let t go from 0 to 4. And that particle moved from the origin up to the point. Well, we calculated what it was. It was the 2 comma 4, right? So that's kind of a nice way to visualize this in terms of motion. The black curve, y equals x squared, we know it is. It was given by our parametric equations. And it's the path of motion of this particle. And the particle moves in the direction of motion as t increases. Because of course, if I let t decrease, it's going to move the other way. But don't be confused by that. The curve only has one direction because the definition is that it has to be as t increases. So the parameter has to be getting bigger. Cool. All right, we'll come back to Desmos, but let's put that away for a second. We can go back into kind of nicer screen view mode. Let's look at a second example. Want to run through the same gambit. Here's some parametric equations. Okay, I've plotted them individually. parabola and a line. But the question is, well, what's the relationship between x and y directly look like? What's the graph in the xy plane? Which way is it, quote unquote, swept out? Okay, so let's try to do that by eliminating the parameter. I'm just going to scroll up a little bit so I have some room to work here. So let me just kind of rewrite the two equations. X, oops, I do that all the time. X is t squared minus 2t. Y is t plus 1. Stop the video and ask yourself which one of those is easier to solve for t. Yeah, I won't pause too long for dramatic effect, but I think it's easier to solve the second equation, y equals t plus 1 for t, because it involves t to the first power. So if I solve that for t, I get t is y minus 1. All right, so then I'm just going to replace t in the x expression to eliminate the parameter, quote unquote. So x is the quantity y minus 1 squared minus 2 times y minus 1. And in some sense, that's the relationship, right? T is gone, but I don't quite recognize the curve in this form. I'm just going to do a little bit of algebra. If I factor out a y minus 1, simplify that a little bit. In this form, I kind of do recognize it. That's a quadratic relationship. I mean, you could see that in the first form too. It's a quadratic relationship in x and y, but in this form, I can see that the y-intercepts are 1 and 3. So it's a sideways parabola, if you like, opening to the right, and its y-intercepts are 1 and 3. All right. So eliminating the parameter, because why do I know all of that information? Well, because I'm way more used to thinking about explicit relationships between y and x than I am parametric relationships. It's certainly possible, and as you gain more experience, you'll be able to look at these parametric equations and know that's a quadratic relationship between x and y. But here it is explicitly. All right. In these parametric equations, I think I kind of passed by the detail above. Let me just write it here again. T here was any real number. So there was no restriction on t, right? So this is going to be the entire parabola, if you like. So if I scroll down a little bit, I've got a graph of it ready to go for us, and I rewrote that information down here. So we just said x is equal to that product, y minus 1 times y minus 3. If you prefer to multiply that out, if it makes it look more like a parabola to you, it's y squared minus 4y plus 3. All right. And then I want to ask the question like, well, what about the direction? Which way is this thing swept out as the parameter increases? There's a couple ways we could answer that. One way is we could just kind of, pick a couple of values of the parameter and compute x and y. What values of the parameter to pick? I don't know. Just pick them so that life is easy on yourself. I'm going to pick 0 and 1, and I got to remember that t increases from 0 to 1, so that's how I'm going to know the direction. So stop the video and do the math. I'm plugging those things into, well, the x equation for x and the y equation for y. So if you let t be 0, the first equation says x is 0, but the second equation says y is 1. All right? So x is equal to 0 and y is equal to 1 when t is equal to 0. So that's right there. So that's where this quote unquote particle is when time is 0, when t is 0. How about when t is 1? The x equation would become 1 minus 2, that's negative 1. The y equation would become 1 plus 1, that's 2. So in the graph here, the point negative 1 comma 2, to me, looks like it's about right there. Okay, so that determines the direction. The curve is swept out that way. Once you know the direction along one piece of the curve, you know the direction everywhere. So that's one way to think about it. Another way to think about the direction here is you could look at that graph of y above, or just look at this equation. Y is increasing as t is increasing. So as t increases, the y coordinates on this curve have to get bigger. Well, that's only consistent with the curve being swept out in the direction that we labeled. If you went in the opposite direction as t increased, the y coordinates would get smaller. Okay, so we got our parametric equations. We eliminated the parameter. We can look at the graph. Let's switch over to check this thing out in Desmos. I wish there was a somewhat quicker way to do this, but it's not too bad. If I can get my finger on that button. So I'm just going to kind of slide this business over here, and I have to select it. So let me pick my second example here in Desmos. Can change the scale a little bit. So you can see that's the parabola we were just talking about. I turned off the axis scale here, so we can't see, but we know that that is crossing the y-axis when y is 1 and y is 3. Yeah, maybe I can turn them back on if you want to see those numbers. It's not, the scale's not locating them there, but I've got my point x of t, y of t labeled there, and I just want to once again show you that if I increase the parameter, direction is correct. That point is sweeping along that curve in the direction that we labeled the arrows. You can still see the arrows over here on the left in the picture. It's down here. Yeah, we labeled this curve as swept out that way, and that's exactly what happens when I'm increasing that parameter. For this particular thing, the parameter is negative infinity to infinity. I can't put that into Desmos, of course. I have it at -4 right now. The point's off the screen, but look, as the parameter increases, we'll finally be able to see the point when it gets into some range. There it is. Nice. And then as t goes off to infinity, that point will just fly off to infinity along that parabola. Very cool. Okay, so there's a couple of examples where we've eliminated the parameter algebraically. For polynomial-like examples, the algebra in those things is pretty telling. You kind of have to solve one equation for t, plug it into the other. That gives you a direct relationship between x and y. Oh, sorry, before we move on, I wanted to point out that, yeah, this function doesn't define y as a function of x. It fails the vertical line test. So this is nice. Parametric equations can describe things where y is a function of x. Here, x is a function of y. In the next example that we're going to look at, neither one of those things will be true. So here's a third example. Parametric equations, I'm taking this from trigonometry. So x is equal to the cosine of t, y is equal to the sine of t. T can be any real number. Here in both of these graphs, I've only plotted t between 0 and 2 pi. That's kind of good enough to know what's going on because cosine and sine are 2 pi periodic functions. Okay, so what do the parametric equations look like here? So I've got a picture of the relationship between t and x and t and y, and you can kind of imagine what it looks like if we extended t off in either direction outside of this first interval from 0 to 2 pi. So the x-coordinate is going to keep bouncing back and forth between -1 and 1, and the y-coordinate is doing the same. And maybe you should stop the video and kind of ask yourself, maybe you can answer this question by some other means. It's certainly possible. What should the graph look like? Which way is it being swept out? All right, let's eliminate the parameter. Let's eliminate the parameter. For these equations, and actually any equations that involve x and y, there's sort of an algebraically superior method for eliminating the parameter rather than solving. Solving either one of these equations for t is going to involve an inverse trig function, which is something that I kind of only do if I absolutely have to. So you can kind of put this in your pocket. When cosine and sine are involved in the parametric equations, I'd first solve them for cosine and sine and then square both sides. So it seems like a little bit of an out of the hat thing to do, but you'll see why I'm doing it here in a second, or probably you already do. Because if I then take those two equations and add them together, well, on the right-hand side, what am I going to get? Cosine squared plus sine squared. But cosine squared plus sine squared at t for any value of t is equal to 1. So here I'm not doing it by substitution, but rather by some trigonometric identity. The parameter gets eliminated. All right. So the direct relationship between x and y in this third example is that the x and y have to satisfy x squared plus y squared is equal to 1. So do you know what curve in the xy plane that equation defines? So that defines the equation. That's the equation of a circle. Yeah, the center of that circle is visible there. Its center is at the origin. Its radius is the square root of the right-hand side. That is, the radius is equal to 1. So x of t and y of t being cosine and sine, respectively, are the equations of a circle. Circle center 0, radius 1 more precisely. So I've got that circle plotted down here for us. You can ignore the left-hand side of this panel here for a second. Here I've just plotted in kind of a static form, cosine of t and sine of t. You know from trigonometry that if you take t to be an angle in radians measured from the positive x-axis, the coordinates of a point on the unit circle of radius 1, is cosine comma sine. So in this example, the parameter has kind of a physical meaning, if you like. You can think of t as the angle in quote unquote standard position. Right, so it has kind of a physical. It's often the case in tomorrow, or not tomorrow. You're watching this on a video, but in the second day of section 10.1, we're going to kind of turn the question around and ask ourselves, like, well, what if you're given a curve first and you want to parameterize it? So if I was given a circle, a natural choice of the parameter would be the angle in standard position. All right. Which way is this thing swept out? Well, we could choose some kind of standard values of t. Say if t is 0, well, then x and y, cosine of 0 is 1, y, sine of 0 is 0. So we're over here at that point. I'm just thinking of t as the angle. I don't have to kind of work hard to think about where I am. I'm not going to choose a whole number here. I'm going to pick pi over 2. If I take t to be pi over 2, then of course I'm going to be at the point 0, comma 1. I know that from my trigonometry. So just like in the unit circle trigonometry, as t increases, this circle is swept out in the counterclockwise direction. Nice. We can switch over to Desmos here, maybe before we do it, so we're just going to be done with this example. A little bit more generally, I'm going to leave the details to you, but if you had parametric equations where x was equal to r times cosine t, r times sine t, here again, t could be any real number, but in order to get this circle, this is actually kind of an interesting thing. As t goes from minus infinity to infinity, you're just going to traverse that circle over and over and over again. So if you just take t from 0 to 2 pi, then you'll just get quote unquote 1 revolution, right? So when you get to be 2 pi, just like in trigonometry, you'll be back at the same point you were at when t was 0, and then other values of t are just going to trace the circle over and over and over again. So if you put a number r in front of there, then you still get a circle centered at the origin, but its radius will be r. I'll let you check that out. Square x, square y, add the equations together, you'll get x squared plus y squared is r squared. Cool. Let's just to go over. I hope it's not making the video too long. You can skip ahead if you're tired of looking at the Desmos pictures, but I want to look at one more time, at least. I just think it kind of looks cool the way that thing pops up there like that. So let me find it. Example 3. There you go. So here I've got my point, my equations. Maybe you can watch the video, but look up at the top, I just typed in cosine of t comma sine t. It graphs the thing for me, and I just want to show you as t increases, that point, sure enough, is going around the circle. T just hit 2 pi. Now it's going around for a second lap. T just hit 4 pi, so it had 2 revolutions. All right. Every time t goes through an interval of length 2 pi, that point is going to orbit the unit circle once. So the equations, x of t and y of t, are cosine and sine respectively. Those are the quote unquote parametric equations of the unit circle. That's really what you studied in your unit circle trigonometry class. You probably didn't use this terminology. I don't know, maybe you did. Okay, let's look at one last example here. One last example just to kind of get you used to what it's like to eliminate the parameter. Here are my parametric equations are 3 plus 5 cos t and 1 plus 4 sine t. Okay, I'm just going to take t between 0 and 2 pi, although the domain could be larger. There's again some periodicity here. So I've just graphed those two waves separately. So I can kind of imagine from these two pictures that x and y are going to kind of circle around something again. It might not be a perfect circle, but x is just going to repeat, oscillating between -2 and 8. The left-hand picture shows me. Y is going to repeat, oscillating between a couple of values. You can figure out what they are either from the wave. Maybe I hope in your trigonometry class that you studied things about amplitude and periodicity and so on in this thing, average value of the wave. So this wave is going plus or minus 5 units around 3. That's where I got the -2 and 8. So this one is plus or minus 4 units around 1. You can determine what those extreme values would be. But I want to focus here on the algebra of eliminating the parameter, okay? So like I said, what you want to do is solve these things for the trigonometric functions themselves. So I'm going to start by solving this equation for cosine. And how would I do that? Well, I would subtract 3 from both sides, and then I would divide that equation by 5. So if I did that, you can stop and do the algebra in your own style, but cosine of t would be x minus 3, the quantity, divided by 5. Okay, likewise, the sine of t is going to be y minus 1, quantity, divided by 4. So once I've isolated those cosines and sines, then I square them. So cosine of t squared, I'm not going to multiply out this numerator. I'm just going to leave it as x minus 3, quantity squared, would be over 25. Sine squared of t would be y minus 1, quantity squared, over 16. And then I add those things together. So cosine squared plus sine squared is going to be what? X minus 3, quantity squared, over 25, plus y minus 1, quantity squared, over 16. But cosine squared plus sine squared is 1. That's why I isolate them before I square. So if I kind of put all that together and try to make it look pretty, I get the direct relationship between x and y. And depending on how long it's been since you've taken an analytic geometry course, you may or may not recognize what the curve that's defined by that direct relationship is. Okay, so that's an ellipse. I'm just going to scroll down here real quick. You can stop the video if I went too fast. That thing's an ellipse. Its center point is at 3, 1. It's visible from the algebraic equation where I just highlighted. And then an ellipse kind of has 2 radii. In the x direction, this ellipse opens up plus or minus 5 units. So from that center, you can go plus or minus 5 units left or right. And it opens up plus or minus 4 units in the y direction. That's what these denominators tell you. The square root of 25 is 5. The square root of 16 is 4. So it's kind of how wide it opens in each direction. So it's not quite a circle. It's this oblong looking thing. And there is the parameter t here doesn't have that same geometric interpretation. It's not an angle, but points on this ellipse have the form x of t, comma y of t, where x and y are given by our parametric equations. All right. So we're going to end this long video by just flipping over to Desmos one more time. I'm starting to get the hang of it a little bit better. Let that thing wake back up and pick my 4th example. So I just want to talk about the direction. Okay, so check it out. In the Desmos window, you can't quite see it all up there, but I've just typed in my parametric equations, 3 plus 5 cos t, 1 plus 4 sine t. And then with this slider, I labeled the center just so the picture kind of looks nice. And now I'm letting t increase. T is 0, and it's increasing. I'm going to let it get all the way to 2 pi, and by the periodicity, it would just go around and around again. All right. So for these parametric equations, that ellipse gets traced out in that, again, counterclockwise fashion. So some of the things that we can talk about, and we're going to talk about this in day 2 of the lecture, is like, well, what if I wanted that same ellipse, but I wanted it to be traversed in the other direction? How would I alter the parametric equations? Well, what if I just wanted a piece of the ellipse? You know, maybe I just want to parametrize the part from 3, 5 over here to the point that is on its far left, something, comma 1, -2, comma 1. How would I parametrize that? What if I wanted to go this way? What if I wanted to go the other way? So those are questions about, given a curve, how do I find parametric equations for it? How do I parametrize the curve? But that's going to be in part 2. Okay, so thanks for listening.